Welcome to the Real Estate Espresso Podcast, your morning shot of what's new in the world of real estate investing. I'm your host, Victor Minash. On today's show, we're talking about a structural failure on 42nd Street in Manhattan. This made headlines all over the world. Now, the building in question was originally an office building belonging to Pfizer. It's now in the process of being converted into a residential apartment building. It's the largest office to residential conversion project in U.S. history, and it will result in nearly 1,600 apartments. Part of the development plan called for increasing the height of the tower by 19 more stories. That's an entire building on top of a building. Now, I downloaded the plans for the new project since these are publicly available. Most of the news stories that are covering what happened are focusing on two structural columns which partially buckled on the 22nd floor of the building. One of the senior executives for the developer made a public statement stating that the columns in question were undersized. Now, of course, there's going to be a detailed investigation, and I expect we'll examine all aspects of the structural design, the materials that were used, the sequencing of the construction, and it's entirely possible that the failure was in fact caused by a design issue or maybe an error in construction, or it could be a sequencing problem that left the building structurally compromised midway through construction. Now, if you've been listening to this show for a while, you will know that my mother was an architect in New York City, and in fact, she was an architect and a structural engineer on another building about a block away from this particular building. My mom was part of the design team on the Pan Am building, now the MetLife building, and it sits on top of Grand Central Station on 42nd Street. Now, in today's show, we're also going to talk about what I learned during my structural engineering classes back in university and how what I learned back then could pertain to this particular failure. One of the assignments we had was to design and manufacture a three-dimensional cantilever space truss that would be capable of carrying a point load way out at the end of a cantilever. Now, the truss needed to be made out of wood, and one of the goals was not just to carry the maximum amount of weight, but rather it was important to maximize the strength-to-weight ratio of the truss itself. An extremely lightweight truss that failed under small load could in fact win the competition if it was light enough. Now, the design project like this is very similar conceptually to the design of a building in the sense that all of the structural elements are dealing with static loads, most of which are based on gravity. But in the real world, loads are never static, they move. And I learned a great deal from that assignment, not just from my own project, but also from the other engineers in my class. In almost every case, the failure was the result of deflection. So when the shape changes, all of the calculations that you made for your original shape are no longer valid. Loads that were designed to be distributed symmetrically are not symmetric any longer. One column might experience less than the rated load, and maybe the neighboring column would be massively overloaded. Well, the same thing can happen in a building. The structural design of the building is based on several factors. The first, of course, is gravity, the weight of all the levels of the building that are being supported above the current level. The second are the lateral forces that result from the wind pushing the building sideways. These are usually handled with shear walls or diagonal bracing elements that prevent the building from deflecting sideways. And frankly, this is where most structural engineers get it wrong. The assumption is that if the wind is blowing from one side of the building, you've got a zone of high pressure on one side and a zone of low pressure on the opposing side. And intuitively that makes sense. The wind tends to flow in a straight line. But in a dense urban environment with lots of surrounding buildings, the wind can and often does go in circles as it makes its way around the neighboring buildings. In fact, there's many examples of structural failures in New York City where the wind can and often causes a building to twist like a corkscrew rather than just trying to bend to the wind on one side. When that happens, the structural columns in the corners are the ones that experience the most stress. They're almost always the ones that fail first, and we've seen examples of windows breaking in buildings where locations that were not even on the windy side of the building. All of that was happening because the shape of the building changed in the presence of wind loading. This deflection is almost identical to what we observed in my engineering project. Some structural members carried much lighter load than expected, and then that asymmetry transferred more load to some of the neighboring structural members. Now, the third element, which is also important, especially in New York, is vibration. All of these buildings are surrounded by subway lines and railway lines, many of which pass directly underneath some of the buildings. These vibrations over an extended period of time can cause structural failures as well. Now, I personally doubt that vibration was a factor in this failure at all. I'm guessing when the investigation is completed, the culprit will be some combination of errors. It's rarely a single error that causes a failure like this. Now, if I was conducting a forensic structural review, I would want to examine, of course, the original 1960s vintage design system. Was the tower designed as a steel moment frame? Did it rely on braced bays? Was it a reinforced concrete core? All of these different elements. How was the vertical addition designed to transfer wind loads? Were new shear walls introduced? Were the existing cores strengthened? Were collectors added to transfer diaphragm forces? All of these things would want to be looked at. And then, of course, we want to look at the construction sequencing. Were temporary braces removed before the permanent lateral system became continuous? Was the structure temporarily relying on incomplete framing? When you convert an office building to residential, there are thousands of perforations for plumbing and mechanical systems, and that can reduce diaphragm stiffness if it's not properly reinforced. Residential conversions require substantially more slab openings than office buildings. What load redistribution would have been designed if the columns were strengthened, if they were strengthened in phases? There might be some temporary deformation that could create secondary bending. There might be differential stresses between new and old framing that introduced unexpected stresses. New modern buildings want to take all of these things into account, including the possibility that there would need to be redundant paths for loads to be transferred if deformation of the building occurs. Now, I'm going to bet that wind was a contributing factor. If you look at the weather on the day of the failure, the wind was light. It was ranging 5 to 7 miles an hour out of the northwest. Hardly the conditions that would damage a building. So let's look further back in time. It was not much wind for several days, but if you go back to July 3rd, there was an extreme heat and humidity event with temperatures hitting 100 degrees in Central Park, and then a cold front began colliding with the heat dome over top of New York City, and that triggered powerful afternoon and evening thunderstorms across the city. It brought damaging wind gusts that caused localized power outages for over 17,000 New Yorkers before it calmed back down. So July 3rd, of course, would have been a construction holiday in observance of July 4th weekend. Then, of course, the 5th was the Sunday, and then the failure occurred on Tuesday. It could be that the damage was in fact caused on July the 3rd, and it didn't become apparent until the 7th. I'm going to bet that when the retrospective is done on this failure, it's going to be related either to something in construction where proper wind loading was not handled, or a fundamental flaw in the design, again from a wind loading perspective. I will report back once the engineering investigation is complete. As you think about that, have an awesome rest of your day. Go make some great things happen. We'll talk to you again tomorrow.